Hey there, peeps. What we're going to look at today is a process that will show you how to analyze situations involving the force of friction. Okay, we're going to actually cover two cases. The first case will be a kind of vanilla case where we've got a force applied that is horizontal, that is parallel to the horizontal, so we don't have anything to deal with in terms of angles, but then we're going to evolve to that where we have that force pulling at an angle, and we'll see what additional steps we need to take to break that force up into horizontal and vertical pieces and to see how it affects things like the normal force. So don't panic with angles. They're really kind of straightforward stuff. It's stuff we've been dealing with all along. It's something that is just common to everyday practice. We have angles, we will deal with them. That's how it is. But let's do the simple case first. Analyzing situations involving friction. A crate with a kitten perched at the top is pulled horizontally with a force of 120 newtons. The coefficient of static friction is mu s, and it's between the floor and the crate, it's 0.5. The coefficient of kinetic friction, mu kinetic, is 0.25. What we want to do is determine the force of friction in each case and the acceleration of the crate while sliding, and we're given that the mass of the crate and kitten system is 10 kilograms. So together they're 10 kilograms. We've got a couple of relationships that will help us determine the force of friction static, in that it is mu static, so the coefficient of static times force normal. So we'll have to find force normal, I would imagine, since we're given mu static. The other case is that the force of friction kinetic is equal to mu kinetic times force normal. So force normal is going to help us in multiple situations for both cases, static and kinetic. So that's what we'll end up doing. Let's do it. First thing we got to create is free body diagram. So here we go. In order to do that, first, I've established coordinate system. Up is positive, to the right is positive. Horizontally, I've created a little picture of the situation. There's our kitten hanging out in the crate. Could be rubbing its butt between it and the crate. That's not the friction we're really interested in, though. But the kitten goes mew, and together it's 10 kilograms. Look at the mu in here. Look at that mu. So cute. We got the nubbies, though, to worry about between the crate and the floor. That's the coefficient of friction we were given. If we asked very nicely of the mu crew down in Antarctica, they would maybe give us this mu between kitten and crate, but we don't have that. So that's for further research, I guess. Here's the 120 newtons that's pulling to the right. And so the free body diagram is going to guide us. So here it is. I've done it for us already to save a little time. What we have here is the force applied. The pull will be to the right, and the force of friction will resist it. This is a resistive force. It's going to oppose the pull. You guys noticed this in the mu of the shoe lab, that the force of friction was getting in the way. It was resisting your pull. That's exactly what it was doing. So we expect that to happen over here. That's the horizontal set of forces, the only horizontal ones, force applied, force friction. And vertically, we've got the force of gravity pushing down on the surface. Notice that there is a surface here, the floor, of course. And pushing up on the crate cat system is force normal. No other forces are involved. We don't have any angles to take care of, so this is the case. So what we've got to do is actually write this out in terms of Newton's second law, which is the sum of the forces equal mass times acceleration in the horizontal direction, mass times acceleration in the y direction. Let's take the horizontal case, okay? Well, force applied is positive, so we'll put force applied down here, and the force of friction is negative, and in this case, that would be the case whether it's kinetic or static, so I'll just write it as minus force of friction. These are the only two forces involved, and they equal mass times the acceleration. Now, in other words, the net force here, force applied minus force of friction, is going to possibly accelerate this mass. Now, we'll get into the little nitty-gritty of when that happens. It's only going to happen in the kinetic case because that's when we find that there's going to be motion. Would not happen in the static case because by its nature, static means standing still, so the acceleration would be zero. When we have the vertical direction take into consideration for some of the forces in the y direction, equal mass times the acceleration in that y direction. So what we have here is in the positive, we have this equals force normal minus force of gravity, Fg. And believe it or not, if there's a normal force, well, what's the acceleration vertically? If it's resting on the surface, it can't be accelerating vertically. By definition, it's going to be on the surface. So therefore, if we think of the physics, A is going to be 0 in this case. So we'll go like that. And so this equals 0. And in this simple case here, we got the force of gravity equaling force normal. Like this. Okay? So that's a little arrow here. Let me just get rid of that. Force of gravity equals force normal. What is that value? Well, force of gravity, as we know, is mass times the acceleration of gravity. So we've got 10 kilograms times 9.8 meters per second squared acceleration due to gravity. Now, yes, I could see that it's negative, right? But that was taken care of over here. I'm not so concerned about plugging in here as I am when I'm writing these equations down in terms of the coordinate system. Now, I'm going to put negative 98 newtons as the value, and that the force of gravity will equal force normal. Does that mean, this is where the signs kind of get confusing, but it really shouldn't be, because we've taken care of the signs of writing the equations down. The only reason why force normal equals force of gravity is because it was positive and force of gravity was negative. But we brought it over to the other side to get force of gravity equals force normal. All right. So this is 98 newtons. So it's important to think of the physics more importantly than to just say, oh my gosh, this is down, it's always going to be negative. Don't get into that mistake where you're just plugging in negative 9.8. Think of what the situation is here, and then maybe you've done some algebra and you don't want to do the double negative thing that can definitely happen. All right. So this is where the negative is. You only do that once. That's what I'm trying to say. Okay, so now we kind of got everything we need to move on to the next situation, and that's using these equations for static and kinetic. So one of the questions was, what is the force of static friction? Well, here we go. Force of static friction is mu static times force normal. We just found the force normal. It's equal, in this case, the force of gravity, because it's responding to the weight of the kitten and crate system and pushing up on it. So we have 0.5 times 98 newtons. And so the amount of friction that will try and resist the pull is 49 newtons. So let's think about this for a moment. What does that mean? This means that the crate will not move unless force applied is greater than force of friction static. I put it, just to be clear, that it's in the x direction over here. So what does that mean? Well, it means that if you don't have enough force, if you don't have, in this case, 49 newtons, it won't move. Object will resist, 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 and won't even move. You must exceed that 49 newtons in order to get this thing into the kinetic range, okay? Fortunately, in this case, we're given that the force applied was 120 newtons, okay? So we're clearly, force applied in that x direction is greater than 49, and we're good to go. This thing will accelerate. So we know that at first this will resist up to 49 newtons, and then it'll start sliding. Okay, and there might be cases where this value is too low and it wouldn't move. All right, so now we're looking at kinetic friction. Force friction kinetic is equal to mu kinetic times force normal. The mu for kinetic friction, the coefficient of static friction, coefficient of kinetic friction is 0.25 times 98 newtons, we get 24.5 newtons. So that's the force that will be resisting while it's pulling in the kinetic range. So the 120 newtons is going to compete against this 24.5 newtons, and because it is greater than 24.5, it will accelerate. To keep it moving though, let's say we let up on the force. Obviously 120 newtons is way more than 24.5, but if you let up to 24.5, it would move at constant velocity. It would no longer be accelerated. So if you dip below 24.5 newtons, what that means is that you would have to, once again, exceed 49 newtons to get it started again, to restart. All right, so this is the minimum to keep it going. So if your value happens to fall, Can't fall below this, otherwise you have to get back to your 49. Keep it going. Well, let's solve for acceleration now. Sum of the forces in the x direction equals mass times acceleration, Newton's second law. Acceleration, if we solve for it, it's the sum of the forces in that x direction divided by m. Well, what were the first forces in the x direction? Force applied, underscore x. It's not a minus, it's underscore, just to, again, be very, very explicit and clear. So we have force applied in the x direction, minus the force of friction kinetic. Well, that's 120 newtons, force applied, minus 24.5 newtons, okay, over 10. So what we have here looks like is this 95.5 divided by 10. We have an acceleration A of 9.55 meters per second squared. All right, it's pretty rapid acceleration of that crate. Hopefully the friction of the kitten is strong enough in itself to stay on. We'll do some demonstrations that will show you situations where it might not be the case, so to speak. But I think the kitten also has claws, so it can dig in if it needs to. So it's not just its body hanging out on the crate. So it'll be fine. I'm sure the kitten will be fine. Okay, let me give you a chance to take down those notes. 3, 2, pause. 1. And that's what it is. Next case, let's look at the angle, an angle pull. And just basically the same steps, just a couple of things to take care of in terms of force normal, force applied, and we're good. Okay, this is Morad, and meow out.